In this lecture, I want to continue our discussion of kind of fundamental transformations in biochemistry and really more fundamental aspects than the reactions this time. I think we covered those. Before I get into that, I want to start with a correction. And that was, I can't believe I missed it. That was the structure of PLP. The PLP cofactor is actually an aldehyde. It can form an imine under certain reactions, which is helpful in the production of amino acids. I like to draw the protonated nitrogen. OP is correct. OH, methyl, that's all correct. But up here we have an aldehyde. So this is actually PLP, and that can get converted with an amino acid. It's actually like a sacrificial amino acid into the structure that I provided. So this is correct. We'll talk more about PLP towards the end of the semester, like maybe the last day or something. But that will then convert into an amino acid into an alpha keto acid and give rise to PMP. Okay, and this is pyridoxamine. Phosphate versus pyridoxal phosphate. Okay, so that's that correction. Now what I want to talk about is prochirality, as this was a topic that was discussed in chapter 2 of the reading, or chapter 2 of the textbook. So prochirality is kind of a way of understanding and labeling things that could become chiral. So prochirality means before chirality. Okay. So where you often see this is in the context of carbonyls. Okay. So carbonyls, we say we have kind of, well, it's not chiral, but it could form stereoisomers. So if we add some sort of nucleophile, we could form a product where the nucleophile is in the back, a product where the nucleophile is in the front. And both of these are chiral. Ethyl group here. Both of these are chiral. And so it would be nice to know if we could sort of label the front and back attacks or the front and back faces of the molecule, because these both lend themselves to different chiral products. So in this upper right case, I show the nucleophile adding from the back side. The other face I showed adding from the front. So what we do is we use a designation called Ray and say, I think it's C actually, Ray and C, or little r and little s to label prochiral faces or prochiral atoms within a molecule. So you'll see this kind of, but what this would look like is if we had our ketone and we just arranged it this way where the ethyl group is on the right. If we label the oxygen 1, ethyl group 2, and methyl group 3, hopefully those priorities don't seem too outlandish, oxygen being the heaviest element, and the ethyl group beats the methyl group. If we circle around, it kind of looks R, but it's not R because we don't have 4 faces. We don't have a chiral center. We've only got 3. So it's kind of like R. It would be R if the OH was in front and the number 4 position was in back. So what we call this instead is Ray, which means like a prochiral R face. Now, I don't want you to worry about whether or not that's going to lend itself to an R stereoisomer or an S stereoisomer. That stuff depends on the nucleophile it's adding or what happens to the molecule. It's just a way of designating that face from the opposite face. So To go to the opposite face, we'd kind of turn the molecule around to bring that face in front of us. We go 1, 2, 3 this way. Now, if we connect 1 to 2 to 3, we're going counterclockwise. So we call this a C face, So this is the prochiral, like S face of a molecule. Now, similarly, we can have prochiral elements. And so if we look at our nicotinamide structure, we could say the H that's a wedge and the H that's a dash are both prochiral atoms. So this prochiral atoms, we could use the same kind of designation. Let's label the atom as 1. This group gets 2, and then this group gets 3. This would be the pro S atom, the C atom, or you could label it as a little s. Oh, gosh. Okay, we're going 1 to 2 to 3. Goodness, one day. Okay, sorry. R all the way around. Pro R atom, the ray atom, or a little r designation. And then you could say the same thing for the opposite atom. Kind of weird format here. Pro S atom. We could have the C atom for that one in the back where we flip everything around. So that's prochirality. It's just a way of labeling things so that we have an understanding that two things are sort of enantiomeric in terms of their face or their position in the molecule, but they're not yet chiral. Now, it's important to note that when atoms have like a ray or a C atom, it could give rise to different stereoisomers in products that it reacts with, especially in this case where we're transferring a nucleophilic hydrogen atom. Another stereochemical term that we could talk about in length, but I'll keep it quick, is the epimer. Epimer is an important term. You hear it quite a bit. It's two diastereomers that differ by only one stereocenter. So if you remember, diastereomers differ by some, but not all stereocenters. Here, epimers in particular, they only differ by one stereocenter. Okay. A lot of the chapter talked about functional groups in biology, or like these classes of biomolecules. We're going to save those for the particular chapters that actually go through those biomolecules in more detail. So I'm not going to cover those right now, and instead I'm going to focus on some of the other topics. And I guess I could give you an example of an epimer. Goodness, that would be good instructional activity. Okay, so let's say we've got a carbohydrate. Okay, there's beta glucose versus, I don't have the name of this, but let's change this position to, instead of being equatorial, it's axial. We would say that those two structures are epimers. Goodness, E. These are epimers of each other. And we could also look at the alpha glucose, where we switch the anomeric carbon. Those are epimers. So these are diastereomers of each other that differ by only one stereocenter. Turns out it's pretty prominent in these multi-stereocenter molecules. Okay. Next, I want to talk generally about enzymes. So enzymes are the catalysts of biology. And the more you think about enzymes, the more you just think, my goodness, these are sort of everything in biology. They're the transistors that make things go. They're the ones that control the zeros and ones that make these biological machines actually operate. I remember when I first really started taking advantage of learning opportunities in biochemistry, I thought a lot about how DNA was so important. And it is. It's all just important. Nothing has to be the most important. But it's nothing without the enzymes that can catalyze the disassembly, the transcription, and ultimately the translation of the code written by DNA. And then when it's replicating and copying, it's those enzymes that are polymerases that are churning out the copies of the DNA. So the enzymes just are so central to life. It's unbelievable. But again, it's not a competition. We're just trying to understand everything so we can create effective and change for society. Okay, so enzymes are usually proteins. I say usually proteins. We can have RNA, and these are called ribozymes. Such a fun word. And some people, there's some hypotheses out there about these being responsible for the origin of life, and that's the RNA world hypothesis. Okay, so these are catalysts. They speed up the reaction. Okay, they're consumed and regenerated. But they do not alter the equilibrium of a process. So they don't alter the equilibrium of an overall reaction. Now they speed up a reaction, and the rate acceleration is not on its own catalysis, but it's the most useful aspect of catalysis. So rate acceleration can be, there are usually about 10 to the 6th rate acceleration. So 6 orders of magnitude, can be as high as 10 to the 17th. And I mean, they can be as low as slightly greater and calling it an enzyme. Okay, that I won't worry about the low end of that because we can go as low as we want to go. I mean, I guess you could slow it down, but those aren't catalysts anymore. Those are inhibitors. Okay. Now, the way this works is you're going to take a starting material and watch it go to a product, right? Except the issue with just taking a starting material and letting it go to a product is that it's slow. So let's add an enzyme. Does adding an enzyme just make it go fast? Well, sort of. It also sort of creates a new pathway where first the starting material engages with the enzyme, which I'm going to call that E, to make a starting material enzyme complex. That has a rate constant, that has an equilibrium constant on its own. So we've added the enzyme and made a substrate enzyme complex. Now we're going to really push the arrows and make things fun and convert that starting material into a product. So hooray, the product is formed, right? Well, the product is usually sitting deep within the active site of an enzyme. And so while the starting material has been converted to the product, it's still adducted with the enzyme. And so what we need to do is dissociate that enzyme from our product. Got my plus enzyme and the minus enzyme on the wrong side of the arrow. Okay, there we go. So the rate at which starting material in the enzyme complex is converted into product in the enzyme complex is called K2. And then when we lose that enzyme, that's called K3. Now, there's several kind of ways of studying the kinetics of an enzyme catalyzed process. Many of those are mechanistically interesting. We're going to kind of keep it simple because biochemistry can show you the depth of Michaelis-Menten kinetics. We're just going to look at K2 and K3, and these are little k's. These aren't equilibrium constants, so I think I usually put my hats on these. We should probably do that here. Okay, K2 times K3 equals the catalytic rate constant. It's also the Tn, or turnover number. Those two things are synonymous. Now you might think to yourself, and you would be right to think to yourself this, okay, I get that, like, I see that there's 3 processes, the enzyme adding to the starting material being converted to product while it's still adducted with the enzyme, and then the enzyme and product dissociating from each other. So those are 3 processes, each with a rate constant. Okay, I'll accept that the K cat that we want to pay attention to is just the product of K2 and K3. I get it. But why is that the turnover number? Well, the turnover number is the number of starting materials converted to product per unit time. That's just a rate. Okay. So that's just a rate. And so we're just kind of using that in the context of the starting material with the enzyme. Now, why are we ignoring K1? Well, we usually, when we're studying these, we may look at saturation kinetics where we add so much starting material that we assume it's all sort of as much enzyme as we have is adducting to the starting material. So we're really focused on how efficiently the enzyme is converting that starting material into catalyst. So we're ignoring that kind of binding preference. We can look at the binding preference with what's called the Km, or how effective our substrate is to bind with the enzyme. So that's a different parameter. So we're not going to focus on that right now. But I mean, what's interesting about that, and let me just mention just some things. So Kcat is usually about 10 to the third, okay? So that many, and just another kind of number that we've looked at is the total turnover number. This is the total number of products formed with a given amount of enzyme over a certain amount of time. And that's usually like where the time is the entire reaction length, as opposed to an arbitrary second. So this is like saying we set up an experiment, or the enzyme is going to do its thing over the course of its life. How many total times does it turn starting material into product before it denatures and falls apart and slips back into the nether? Okay. Now, what's cool about enzymes is the way they accomplish their task of rate acceleration is to drop the activation energy. Okay, well, that's not cool. That's just how catalysts work. They decrease the activation energy of a process through a number of ways. Enzymes typically stabilize transition states. And if you stabilize something, you lower its energy. So when I say there, I mean the transition state energy and activation barrier. Okay. So now the energy required to accomplish the reaction and how likely the reaction is to occur are, I guess, much less and much greater. The reaction is more likely to occur and it occurs more quickly. What this looks like from an energetic standpoint is if we have a reaction coordinate and an energy, so let's put energy over here, and then reaction coordinate along the x-axis. What that looks like is if we have starting material here, and let's say it's a really slow process, and like a lot of biological reactions, it's not hugely exothermic or endothermic. It's pretty close, which we have to deal with, and we'll talk about that in a second. This is the uncatalyzed reaction. And now if I go blue for my catalyzed reaction, the first thing the starting material does is it goes over a smaller hump to form the starting material plus the enzyme. The enzyme stabilizes the transition state for the formation of product, but the product is still coupled with the enzyme. So then we have to overcome a last transition state energy to give rise to our product. So this would be K1, K2, K3, and this would be Kcat. Okay. So what we've done is we've taken our energy diagram, which had a huge hill, and just kind of burrowed through the middle. We actually make a new transition state because we're adducted to the enzyme. And the enzyme is so good at stabilizing that new transition state that it just sort of evolved and was built to capture that transition state, to distort the molecule to make sure it's ready to go, and really promote that reaction. In fact, the book mentions that in many cases, enzymes bind so tightly to the transition state that they bind tighter to the transition state. I realize this is an awkward sentence, sorry. To the transition state geometry than the starting materials and products. Well, the products is not surprising. We want to release those and form the products. Products are always good substrates for enzymes, but let me just back up a second, okay? Starting materials are these things that exist in nature, these things that our enzymes that have been evolving have spent more time around, but yet the enzyme binds more tightly to this super awkward, super high energy transition state intermediate. Thereby, as it binds, it stabilizes, gets lower in energy, and makes the reaction more likely to occur. Now, what we kind of started the lecture with was talking about PLP, and that's an example of a cofactor. So enzymes use cofactors, which are small molecules and metal ions. I think I've mentioned those a few times. And these are our vitamins and minerals that we need in our diets. But these sort of stack the deck. That is, they are kind of the thing that does a lot of the heavy lifting within the enzyme. So they're a key part of the enzyme active site. They accomplish a lot of the chemistry. The chemistry, though, wouldn't be possible without the enzyme supporting the cofactor. So that stack the deck, that was a term I heard some famous enzymologists kind of throwing around as they were describing evolving new enzymes. They said when you can evolve new enzymes around a cofactor, you can stack the deck in terms of the type of chemistry an enzyme can do. Okay, so some examples would be PLP, NAD plus, CoA, biotin, SAM, ATP, GTP, all of these things work together. Okay, speaking of ATP, ATP is all the rage. It's the way that we kind of generate energy for the reactions. If you look, the cell biology is able to accomplish chemical reactions using enzymes to decrease the activation energy, but it doesn't affect the thermodynamics. It doesn't affect how likely something is to proceed in terms of just raw energetics, right? If we're exergonic or if we're endergonic or endothermic, we have to pump energy into a system to make the reaction go. So how do we handle this? Well, in the last section of the chapter 2, they talked about high energy compounds or molecules and coupled reactions. And here is where we use molecules like ATP, and if you replace the adenine base with guanine, you get GTP, but it's the same principle. These have a high energy bond. Now, what this means is if it's a high energy bond, that means it releases a lot of energy when new bonds are formed in its place. Okay, now that's an important idea. So a lot of times when I learned ATP, I was taught, ATP is high energy, so it just releases energy when it reacts. Now what happens is when it reacts, two things happen. Anytime a reaction occurs, bonds are formed and bonds are broken, right? Well, breaking of bonds costs energy, okay? It takes energy to break bonds. We know that, bond dissociation energy, okay? We look at how much energy we have to pump in to break things. So we break bonds, costs energy. Now here's the idea. With ATP and other high energy molecules, because we're so high in energy, those bonds are cheap to break. That is, they don't cost that much energy. They still cost energy. It costs energy to break the weak bonds in ATP. But here's the thing. The new bonds that result are so much more stable. And anytime you make bonds, you release energy. So the new bonds that we make are so stable and release so much energy in the surroundings that it exceedingly overcomes the low cost to break the corresponding bonds of ATP. Okay, so that's just kind of an aside. But what these do, ATP, these undergo a favorable and overall lysis reaction with water. Now what happens is if you take water and you add it to ATP, you get PI plus ADP. Okay. And we'll define what each of these are in a second, or you can react this with acetate and ATP to get an acyl, or acetyl in this case, phosphate plus ADP. Okay. So now let's break this down and look at some, look at the actual structures. Okay, so here's ATP again. ATP is adenosine triphosphate. So adenosine is ribose with adenine. So that's adenosine. And what I want to focus on is the TP, which is the PO-PO-P arrangement of phosphate groups. Okay, so we have phosphate 1 bound to another P. Whoop, need a bond there. O, P. There's my 3 phosphates. Now this O is bound to ribose, which is bound to adenine to give overall adenosine triphosphate. Okay, so we have our 2 carbonyls, we have our 2 O minuses. Okay, so ATP turns out to be a pretty high energy molecule, and a lot of it has to do with the fact that we have so many negative charges close to each other, a lot of repulsion here. The bond that we're going to focus on is this bond here. This bond here is weak. Now, the reason why I say it's weak is because if you look, we have this diphosphate leaving group. And perhaps we could break another bond to make inorganic diphosphate, but this is typically the bond that breaks in the reaction with water and acetate. Okay, so or any other like nucleophilic oxygen. Okay, so what happens here is if we have O on our nucleophile, O on our nucleophile is going to consider whatever, some lone pairs. It's going to add to the phosphate at the end, and we're going to get like an addition elimination sequence. We've got a ton of O minuses, but now we've got our O nucleophile. I'm going to abbreviate, well, I mean, I'm already this far. Okay, so now we're going to come down and come over here. And that's going to make 2 molecules that are much more stable than the ATP that we started with. Yeah, okay, that's right. Okay, so we broke that bond. We made a nucleophile on oxygen bound to a phosphate. And so this is what we typically see that happens. And this is very exothermic. This is going to release a lot of energy. And so what ATP does is it kind of comes along for the ride with a lot of these reactions to release energy to overcome any thermodynamically unfavorable events. Okay, so energetically, we can actually quantify the numbers we get out, and we show that when ATP is around, those numbers become a lot more negative and a lot more spontaneous. And that's because the exothermic process that occurs when ATP breaks down in the presence of some nucleophilic oxygen. So that's speaking energetically. Let's push some arrows to show how this can be the case in a productive standpoint. So a really nice example from the back of the book showed that an important reaction that we may want to do is to make acetyl-CoA. So this is an super important reaction. Now what it involves is a CoA cofactor. So this is coenzyme A. It's super big. It's got an adenosine diphosphate hooked up to a multitude of groups, but let's just draw this sulfur atom on a I'm just going to write the rest of CoAs here. The sulfur atom that's on CH2 nitrogen. Okay, so what we want to do is we want to couple that with acetic acid drawn as the conjugate base as acetate. We want to couple these things together to get acetyl-CoA. Okay, now this process is challenging to say the least. Okay, first of all of the carboxylic acid derivatives that are present, carboxylic acids are some of the worst, and carboxylate ions are the worst electrophiles in addition elimination sequences to generate more carboxylic acid derivatives. This is a terrible electrophile. Why is it a terrible electrophile? Because it's actually a good nucleophile. We want sulfur to be the nucleophile to add to it like it's an acid chloride, which isn't going to happen. So what do we do instead? Well, this is an unfavorable reaction as it stands. But what if we couple ATP to it? And you're like, okay, couple ATP. Does that mean I have to like calculate the energy lost when ATP reacts with some sort of nucleophile? Yeah, but we can actually push some curly arrows to make it seem a little bit more interesting. Let's do this. Let's go with ATP here. So with ATP, I'm going to take that carboxylate ion, which in this case, it's acetate, the acetic acid conjugate base. And I'm going to say, yeah, it's a terrible electrophile. You know how I know that? Because it's a great nucleophile. This is a nucleophile. Well, what we can do is we can couple that with ATP. Namely, I want to emphasize it's the exterior phosphorus that's electrophilic in most ATP reactions. Okay, you don't have to draw all of this if you look. I ran out of room. No. Okay, so it's this bond right here that we're going to focus on breaking. Now, the way that's going to happen is the nucleophilic oxygen of acetate is going to add to the phosphorus on the end of ATP. We could draw some tetrahedral intermediate. Okay, now that's going to come down. Oh, I got my acetate here. And kick off the diphosphate leaving group to give rise to ADP, adenosine diphosphate. Why is it diphosphate? Well, it lost a phosphorus atom. What happened to that phosphorus atom? Well, it became this. What is this that I'm referring to? This is an acyl phosphate. feel like I went up too fast. Acyl phosphate. This is now a great electrophile. I said when I had my scale of things that undergo acyl substitution reactions, the acyl phosphate was the best in a biological medium. And so it's formed by taking acetate and just reacting directly with ATP to make ADP. Okay, so it's this acyl phosphate that will react with the sulfur atom of coenzyme A by way of additional elimination sequence to make the thioester. And I feel like I want that to add as the SH. So it's going to add to the carbonyl oxygen, giving us a tetrahedral intermediate that has a methyl group and a phosphate that can collapse down to make what's called inorganic phosphate, which is just phosphate that's sitting by itself. And I'm also going to lose the sulfur atom, if you don't mind me losing that in the same step. And now we've got acetyl-CoA made ultimately from acetic acid, but we just had to use ATP to get to a reactive intermediate that could undergo the acyl substitution reaction. Now we could go through the numbers and show that this is a thermodynamically favored event. So that's just one way. And you see that we form, I should have defined this earlier. This is PI, which is inorganic phosphate. Okay. Other ways that you can kind of use ATP to drive reactions is you can do just a reaction that generates inorganic phosphate and then have something that carries inorganic phosphate away. So Le Chatelier's principle drives you forward. So an example would be, well, I can't think of an example off the top of my head, but and so you can use ATP in a number of ways to drive reactions forward, given its instability, but also it's so readily available in biological systems because there's so many methods for cranking out and converting inorganic phosphate and ADP back into ATP. Okay, that's a discussion for another day. We've spoken long enough, and that'll cover chapter 2 minus the functional groups. So next week we'll look at terpene biosynthesis and a lot of stuff related to the biochemistry of fats and waxes. So until then, I'll see you next time.